Caramel. It's more than just a delicious candy. It's an experience, a universal language of sweetness that speaks to the heart and soul, and taste buds. From the golden drizzle atop a rich latte to the crackling shell of a creme brulee, it's undeniable that caramel is a staple in the food industry. But the process of creating it is more complex than it may seem. To understand caramelization, let's first take a look at what exactly caramel is. Caramel is sugar that has been melted and then cooked to a specific degree. Caramelization refers to the process of turning sugar into caramel. This is one of the oldest chemical reactions in cooking, as though the exact date of discovery is unknown, it is likely that caramelization began around the time humans started using fire for cooking, over 10,000 years ago. Some early evidence of caramel includes in Southeast Asia around 4000 BCE, where people began experimenting with sugarcane to create sugar, and in the Middle East during the 8th to 11th centuries, where the first caramel sauces and syrups were made. The original discovery was probably accidental, however, now it is widely used in the food industry. Some examples of popular foods that utilize caramel are creme brulee, popcorn, candies, ice cream, cheesecake, and many, many more. Caramel is usually made with white granulated sugar, or table sugar, which is composed of an organic molecule called sucrose. One molecule of sucrose contains 12 carbon atoms, 22 hydrogen atoms, and 11 oxygen atoms, so its chemical formula is C12H22O11. Sucrose can be broken down into two simpler molecules, called glucose and fructose, which are structural isomers of each other and have the formula C6H12O6. When eaten, these molecules are converted into energy by the body. So, how exactly do we turn these solid white crystals of sucrose into caramel? Well, to do this, the sugar has to undergo caramelization, a series of chemical reactions that result in changes in the color, texture, and flavor of table sugar, so that it becomes caramel. The first step to caramelization is heating the sugar to high temperatures. The heat is required to kickstart the process. It breaks down sucrose molecules into glucose and fructose. This involves temperatures higher than the melting point of sugar, so that the sugar is not only liquefied, but undergoes caramelization. When the sucrose is decomposed, it is said to have gone through sucrose inversion. Different sugars invert at different temperatures. Sucrose begins to break down at 160 degrees Celsius, or 320 degrees Fahrenheit, as does galactose and glucose. Fructose breaks down at a lower temperature, 110 degrees Celsius, and maltose at 180. When baking, this first step is usually done on the stove, with the sugar dissolved in milk, cream, or water. However, even if the sugar is not in solution, it will still melt down into a liquid. Once sucrose is broken down, the molecules undergo dehydration synthesis reactions. This removes water from the sugars, allowing them to interact and bond with each other and create new molecules. This includes the three main products of caramelization, which give caramel its color and flavor. Caramelon, which has the chemical formula C12H18O9, and two polymers, caramelene and caramelin. Other product molecules of caramelization help to enhance the flavor. For example, diacetyl, which is also known as 2,3-butanedione, forms during the early stages of caramelization and provides a buttery flavor. Maltol creates a toasty flavor. Furans can have a sweet or nutty flavor, and esters and lactones also have a sweet flavor. These are only the most common and impactful products of caramelization. According to the science of cooking, hundreds of different products can be formed, so even if the caramel making process remains exactly the same, the end products may differ. The overall caramelization reaction can be represented like this. Interestingly, the process of caramelization is very similar to another key chemical reaction in cooking and baking, the Maillard reaction. The Maillard reaction is also a browning reaction, however, it involves the cooking of both proteins and sugars, rather than just sugars, which is what caramelization is. Consequently, the Maillard reaction occurs when cooking foods like meat, vegetables, eggs, or baked goods. Both, however, do result in darker colors and more complex flavors. The product of caramelization can be influenced by many different factors to create unique results. Reactions can be altered by changing various factors, which creates new or altered products, in turn changing the properties of the caramel product. There are 5 main factors that can affect the product of caramelization. They are heat, the type of sugar used, presence of water, pH level, and cooking time. First, let's look at heat and heat management, as it is the most influential. If the sugar is overheated, it may burn, losing its sweet flavor and becoming bitter as the sugar molecules are destroyed. If the sugar is not heated enough, the reaction may not occur at all, as temperatures are not high enough for sucrose inversion. At lower temperatures, between 120 degrees Celsius and 170 degrees Celsius, the temperature is high enough for only the beginning stages of caramelization to occur, meaning if caramelization is stopped at this point, the product will be underdeveloped. At mid to high temperatures, the sugars are more reactive as the molecules have more energy. Thus, more reactions will occur, and the result is a further developed caramel product. If temperatures exceed 200 degrees Celsius, the sugar molecules will burn off, leaving only the bitter compounds that have a burnt taste. This caramel is almost always unusable. Overall, low temperatures will create a mild, sweet-tasting caramel that is light in color, ranging from yellow to white, and it will have a thin and syrup-like consistency. Middling temperatures result in deeper, richer flavors, with a golden brown color and thicker, sometimes brittle consistency. At very high temperatures, the caramel becomes burnt and bitter. It will have a dark brown or black color, and it will be very hard and very brittle in texture. The type of sugar used to make the caramel also affects the product. As I explained earlier, different sugars have different caramelization points, so the process of cooking them is different. But they can affect the flavor of the caramel too. As sucrose is the most commonly used sugar, it creates a smooth texture and a classic taste. Another example is fructose. If fructose is used instead, the caramel will be more bitter and sensitive to burning, as it has a lower temperature of caramelization. Water increases the time required to reach caramelization temperatures, as before caramelization can begin, the water must evaporate, which keeps the temperature of the mixture at or below 100 degrees Celsius, until most of the water is gone. It also helps prevent localized burning because the sugar can dissolve evenly in the water. Additionally, the water can affect the texture of the caramel. If water is retained in the caramel, it becomes softer and more chewy, and it becomes hard and brittle if all of the water is boiled off. Next, pH level. An acidic or basic environment can catalyze the reactions during caramelization. This means that the reactions occur faster and at a lower temperature. Acids like lemon juice, vinegar, or cream of tartar increase the hydrolysis of sucrose into glucose and fructose. Since glucose and fructose caramelize at lower temperatures than sucrose, this speeds up the overall process. Additionally, extreme pH levels break sugars down into smaller molecules because the environment destabilizes the sugar's molecular structure, making it more prone to reactions like hydrolysis, fragmentation, and isomerization. The acids, such as lemon juice or vinegar, provide an abundance of hydrogen ions, which act as catalysts in breaking the glycosidic bonds in disaccharides like sucrose. Bases like baking soda supply the hydroxide ions, which destabilize the sugar molecules by attacking their chemical bonds. This leads to fragmentation and isomerization. Lastly, the cooking time can affect the caramel, and this one's pretty simple. If the caramel is heated for too long, it will burn. The longer the sugar spends at high temperatures, the more it will caramelize and turn into a darker color. More water will evaporate, leaving the caramel harder and more brittle. And vice versa, if the sugar is cooked for a short amount of time, most of the moisture will remain and the caramel will be softer. Overall, caramelization is a fascinating process that connects chemistry with an everyday treat. Understanding how these reactions work let us better appreciate their role in cooking and our daily lives, showing how chemistry can turn ordinary ingredients into something delicious and special. Thank you for watching.